you so much, especially for the comment about the board games as I tried to get myself back together after that lovely, oh, now I'm going to do it again. Lovely comments by Peter. Peter, that was really wonderful and moved beyond words. That's very much a treasure. And I'm just going to cry in that week. So it has been a blast all week long. I visited twice before, once at the unit, and this was so much fun because I got to spend so much time with everyone in the unit. I had a lot of time with the students. I was able to be at the end of the goose chase. I got to see all their really excellent work yesterday. And it's certainly the case based on the talks I've heard today and also all the really exciting work that's being led by the students, that the unit is in exceptionally good hands, and I think a bright future is in store. Today I'm going to talk about some work that I have been doing, motivated and very similar, in fact, to a lot of work that Sylvia has done, and I understand she's being honored this evening in London for her really outstanding contributions to the COVID pandemic. So hello, Sylvia, when you watch this later. But talking about using Bayesian learning and clustering to get information about potential disease phenotypes. And this has been work with a longtime collaborator and my husband, David Dunson, as well as two physicians in Duke's Global Health Institute, Deng Madut and Matt Rubach, as well as PhD students, and he gets the yellow highlighting because he's really done the lion's share of this work, Alex Dombowski, who's at Duke University. Alex is actually known in our department as being a really strong theoretician, but as part of this project, he showed us how he's also a really exceptional applied statistician. So I'm really excited to be able to have the opportunity to tell you more about this work. And so the main objective of the study I'll talk to you about today, the sixth study, or Sepsis Characterization in Kilimanjaro study, is to classify sepsis patients in northern Tanzania into subtypes using routine clinical variables. And as a later part of the project, we'll also be incorporating data from host immune profiles. And we hope that this subtyping work will contribute to our overarching goal to improve sepsis recognition and classification, and down the road, by doing so, being able to recognize certain patients are presenting with certain subtypes in the hopes that eventually interventions tailored to subtype can be studied and perhaps implemented. So what's sepsis? So you may be more familiar with the term blood poisoning, which is an older term for septicemia, blood poisoning by bacteria. Sepsis, however, can be caused by a wider variety of infections. It occurs when the body overreacts and overwhelms the system with a toxic response to an infection. Often, when you hear that someone has died from complications of pneumonia or complications of surgery, they've died from sepsis. While sepsis itself isn't contagious, the infections that can lead to it typically are. Now, sepsis plays a major role in the global burden of disease. While age-standardized incidence of sepsis fell almost 40% and mortality decreased 50% from 1990 to 2017, in 2017, there were almost 50 million incident cases of sepsis worldwide and 11 million sepsis-related deaths, which was approximately 20% of all global deaths. Unfortunately, 2 out of every 5 cases of sepsis is in a child under age 5. And importantly, 85% of the cases occur in low and middle income countries. Now, this map shows the percentage of deaths due to sepsis by country, with a very high burden in sub-Saharan Africa. So while sepsis accounts for less than 8% of deaths in most high-income countries, the figures in sub-Saharan Africa largely lie in the 25 to 50% range, and Tanzania itself lies in the 30 to 35% range. Now, to set the stage, we'll be talking about prior results from a very large electronic health records-based study called Seneca. And the Seneca study used data from over 63,000 patients in Pennsylvania. They clustered basic clinical variables to determine 4 disease subtypes. There was an alpha subtype, which were people that generally had a good prognosis, a beta subtype, they were older and had more chronic illness and renal dysfunction, a gamma subtype characterized by inflammation and pulmonary dysfunction, and a delta subtype, which had more liver dysfunction and septic shock. And a few other studies have used immunological markers to determine subtypes as well, and that's something we're working on right now. But note, these clusters aren't perfectly separated. Clustering is actually a really hard problem. And it's still possible there could also be progression in our patients from one subtype to another and back again. So this is a really complex science, as Peter mentioned. I don't know that there's a right here, we're hoping that we're going to find something that will be useful. And so these clusters, however, have provided important insights into possible disease types. So for example, after this study was carried out, the investigators went back and got data from previous published randomized studies that were null. And when they stratified the patients in those null studies by the phenotypes derived in the Seneca study, they found that certain treatments might be beneficial for a given subtype while they were not beneficial in the whole population. So this made people really excited, thinking about perhaps we can do this on a broader scale. Now, things to remember about this important prior study are that one, it had a massive sample size, so we won't be this fortunate in our study. And two, its source population is quite different. So the source population there are older adults in a high-income country. And one challenge for sepsis management in sub-Saharan Africa that's worth noting is that the patient populations and the causes of sepsis are quite different compared to those in high-income countries, where much more of the research on sepsis has been conducted. So in high-income countries, sepsis often occurs in elderly populations with non-communicable diseases. And the most common cause is bacteremia or bloodstream infection. Meanwhile, in much of sub-Saharan Africa, sepsis is occurring in younger, middle-aged adults. There's, of course, the generalized HIV epidemic, and the pathogens causing sepsis are much more diverse. Differences are significant enough that some treatments that have been shown to be effective in high-income settings have harmed patients on average in northern Tanzania. So the sixth study is funded by the US National Institutes of Health, and it's a two-phase study. The first phase, which I'll talk about today, involves using a subset of patients from the INDITE data repository. Now, INDITE was designed to investigate febrile deaths in Tanzania. And so for SICK, we're taking a subset of the INDITE patients. The subset has 288 patients, and they were selected because they meet criteria for likely sepsis using a validated scale. So it's not exactly the same population, but it's close. The second phase is still in the field. We hope to finish recruitment at the end of this calendar year. We have 500 participants currently enrolled, and the idea is to validate the clusters we find in the first phase. Now, a little bit about treatment. Currently, most of these patients are getting about the same treatment, okay? A lot of the same antibiotics, similar amounts of fluid, which we'll note would be much less fluid compared to North American standards, and some will get steroids. Some are not treated. Clinicians are really eager to identify more effective treatments to benefit patients, but this area is really far from settled, even in high-income countries. So for example, there was a randomized trial in the New England Journal of Medicine that raised a lot of hope around fluids, but then in 3 subsequent very large studies, they found that the use of fluids is quite complicated and it was less beneficial than originally believed. So it may be the case that treatment's effective for one subgroup, for example, but not for others. So next steps in our study, once we're done deriving our clusters and we validated them, would be able to take advantage of some of the rich data we have on the treatments and on the course of disease in the participants to explore treatment-specific outcomes by subtype and move in directions of either additional investigation or even perhaps trials to help us better understand subtypes. So features we cluster in the study are based on those measured in this prior Seneca clustering study. And they include clinical signs like temperature, respiratory rate, pulse rate, and systolic blood pressure, inflammation markers like the white blood cell count, C-reactive protein, organ dysfunction markers like aspartate transaminase, bilirubin, blood urea nitrogen, creatinine and platelets, and additional markers including glucose, sodium, bicarbonate, and albumin. So here are the data from a woman enrolled in the INDITE study. Now for interpretability, it may be useful to characterize the woman's clinical and lab values as elevated, highlighted in yellow, neutral, or diminished, highlighted in green. And of course, each patient's going to have a unique profile in terms of the clinical and lab variables of interest. And so here we see 4 INDITE patients, all of whom have different patterns of elevated, neutral, and diminished levels of these 15 features. So using clustering, our goal is to group patients into clusters so that patients inside a cluster are fairly similar with respect to important features, while maximizing the differences in meaningful features across the different clusters. All right, so this morning we focused quite a bit on model-based clustering, and here's a standard model. In the next few slides, what I'll do is walk you through the components, and I promise it's not so bad. To start, what are our data? Our data on participant I for feature J are just the values we observe of 15 observed features. So YI1, for example, would be the systolic blood pressure of participant I. YI2 is the bilirubin of participant I, and so forth for our 15 features. So here P is 15. Now, an underlying idea of the clustering is that people within a cluster, so here I say the cluster for participant I is cluster L, these people will tend to have more similar combinations of values of these 15 observed features than people in a different cluster, say cluster L plus 1. And so thus the mean, mu, and variance, sigma squared, of each feature for each person may depend on the cluster L to which that person's assigned. A typical Gaussian mixture model assumes the observed features each follow a normal or Gaussian distribution, which is parameterized by its mean and its variance. Now we have a Bayesian model, more on why that is in a little bit, and so we'll place prior distributions on the parameters of our Gaussian distribution. So one would typically use a simple independence prior structure for mu and sigma squared. So Sylvia Richardson and Adrian Raftery suggest use of a weakly informative data-dependent prior, making only minimal assumptions about the data. Here are priors for the mean and variance inside a cluster depend on 3 quantities: the range of the variable of interest, the midpoint of that range, and an upper bound on a number of clusters for scaling purposes. So I'll go through this in more detail in a moment. Now, why do we use the terminology mixture model? You've heard that multiple times today, and if you're not a statistician, this may not be immediately obvious. So we expect not to find just one type of sepsis, but several subtypes or clusters. Each cluster occurs with some probability, here represented by the parameter psi. Suppose we find 3 subtypes, a big subtype and 2 small subtypes. So then a reasonable model for cluster membership would be a multinomial model, with a probability of each subtype represented by a parameter, say C1, C2, and C3. And if one's cluster is big and 2 are small, we would expect the probability corresponding to the big cluster to be pretty large, close to 1, and the probability C2, C3 that correspond to the smaller clusters be closer to 0. Now, typically we induce a prior on clustering, not by putting a prior on a clustering structure. So that is something I'm really interested in, and I've done some cool work, fun work with Sally Paganin at Ohio State on that. But instead, what we do is we assign a prior to our weights, this psi vector, and then we marginalize it out. So to finish the specification, we place a prior on the weights. Here we're using the approach of using an overfitted finite mixture model with a symmetric Dirichlet prior on the weights, and we're setting 10 as the upper bound on the number of clusters. So remember, Seneca found 4 clusters, so we're giving ourselves a lot of room there. This will favor fewer clusters, and also that's typically preferred when our goal is clinical classification. So why a Bayesian Gaussian mixture model? So some reasons that we want to be Bayesian here: we'd like to have adaptive selection of the number of clusters, so our model will collapse back down on smaller numbers of clusters to the extent that the data support that. We have some missing data, and so being Bayesian gives us a very natural framework for handling our missing data as part of the analysis. We don't have to drop somebody just because they're missing a lab value, for example, from the modeling framework. It facilitates use of prior knowledge. So here we have several very, very large studies in high-income countries, so maybe not directly relevant, but still very important studies that we may want to include in terms of helping us interpret results, or maybe even in the specification of the prior directly. And also it will facilitate evaluation of hypotheses regarding influential features. And so this is something that Brendan touched about a little bit. We take a slightly different approach, but similar in some interesting ways. And so we'll talk about that too. So I want to take one moment to say a little bit about Bayesian inference. Bayesian methods are a popular choice for fitting Gaussian mixture models. And one nice way in which to take into account the prior Seneca study could be through Bayesian inference. Many researchers like Bayesian inference because it mimics the type of learning or updating we do mentally every day. So for example, suppose a patient without any history of foreign travel tests positive for chikungunya using the rapid diagnostic test, so that's chikungunya. Given your prior knowledge of the extremely low prevalence of this virus in the UK and the sensitivity of the test, which isn't great, if you're a clinician, you'd probably be highly unlikely to make a definitive diagnosis at that point. Maybe you'd be more curious about how they got their hands on a rapid diagnostic test for chikungunya in the first place. So you have a very strong prior opinion that's going to lead you to discount the data to a great extent in that case. But you probably follow up. Something weird's going on. It's worth, investigating more. So of course, most scientific problems are much more nuanced, but Bayesian thinking is often used. So we have prior beliefs, they're combined with the data's evidence in order to update our posterior views on a topic. Now the strength of prior views should be really thoughtfully encoded. And so many situations are appropriate for weakly informative priors. We don't want to make a strong statement about what we think our data will reveal, but in others you might give heavy weight to prior knowledge. And so because I took this slide from Pinnacle, let's say your prior is based on the performance of the English national football team at all the prior Euro championships, okay? Sorry. And your data, okay, that you're going to collect, will be the current team ranking at the time of the next Euro championship. So you might, not saying what you should do, but you might have a very strong prior that's going to prevent you from placing a very large bet on England, regardless of how England's ranked, okay? So not always appropriate to have a strong prior, but occasionally you might want to use them. So when we talk about our prior, it's going to be important to think about the notion of a cluster center. And so with many clustering methods, we get a sense of where the cluster is via what we call centers. In Bayesian clustering, we have uncertainty about the location of the centers, and we model that using a prior distribution. So what we do is we're going to describe that prior distribution as a function of what we call meaningful regions. So we're going to take the structure we had before, the standard Bayesian Gaussian mixture model, and we're just going to reimagine the prior on the cluster mean. So here are the parameters in yellow. Everything else will be fairly standard. If you fit Gaussian mixture models, pretty standard choices for everything else in our framework. The only thing we're playing with here is just the prior on the mean. And so clustering solutions can be really difficult to interpret. So I know anybody who's done clustering has probably struggled with this a good bit. And it can become even harder when you have a small data set like our 288 here. Because our long-term goal is to inform treatment decisions, it would be really nice to have interpretable clusters. And so we're going to address interpretability by placing a prior on meaningful, our prior will be based on meaningful regions. And what do I mean by a meaningful region? This is just values of features that have a clear medical meaning. So for example, if we think about systolic blood pressure, you might say that SBP under 120 millimeters of mercury is normal, 120 to 129 is elevated, 130 to 139 characteristic of stage 1 hypertension, and over 140 stage 2 hypertension, okay? So we could define these as meaningful regions of the feature of systolic blood pressure. And of course, these regions may differ depending on the age of our population and other characteristics. So for this 6th study, we consider 2 different derivations of meaningful regions. The first is based on talking to our clinical collaborators, Matt and Ding, and we asked them to give us ranges of diminished, neutral, and elevated based on a North Tanzanian population, okay? So similar to what we did for SBP, but they're taking into account the population of patients that they're treating. The second notion of meaningful regions that we used was based on the Seneca study. And again, we sat down with Matt and Ding and said, okay, the 4 Seneca subtypes, alpha, beta, gamma, and delta, how would you characterize meaningful regions of our 15 variables in terms of those clusters. So it's sort of one step away from the data. It's saying, okay, this level of SBP is characteristic of the alpha and the gamma clusters, for example, from Seneca. So what's our prior structure? So we call our method clamor, clustering around meaningful regions, and we're going to consider a set of possible values of our feature Yij. So if Yij is systolic blood pressure, you know, right, it could be, I don't know exactly how low systolic blood pressure can get while you're still alive, but certainly it's going to be a positive value and not too close to zero. And then it can get pretty high, right? You know, maybe a little over 200. And then what I'm going to do for that set of all possible values is define a set of intervals corresponding to meaningful regions of the variable. So for systolic blood pressure, it might be less than 120, 120 to 130, 130 to 140, 140 and up. And then we're going to specify the clamor prior for cluster centers using these meaningful regions. So here's the prior, and don't worry, I've got a picture coming up in a couple slides. So we're using expert information to construct the prior. We're trying to construct the prior so that our inferences and our clusters are going to be more interpretable. And instead of setting, for example, a different weakly informative prior on each potential cluster, we're going to collate this information into a simple base measure. So this prior will highly favor cluster centers found in these predefined meaningful regions, and with the goal at the end of the day being to have more directly clinically interpretable clusters. It's going to be a multimodal prior with modes inside each meaningful region. So note this is a prior for cluster-specific parameters. It's not an assumption that our data itself are multimodal. Okay, so this distinguishes this prior construction from some type of approach like mixture of mixtures. And note that the choice of kernel, here we're using a normal kernel because we're talking about Gaussian mixture models. That's flexible, so there's nothing that ties us to having to use a Gaussian. So we can interpret the clamor prior as a way to model cluster interpretation explicitly. Each cluster is linked with a sequence of meaningful regions that describe the characteristics of its members. So here, for example, cluster L is characterized by feverish temperatures, diminished breathing rate, neutral values of bicarbonate, and diminished albumin. So this kind of mimics the post hoc analysis we'd like to do once we found our clusters at the end of the day. So here's an example of the clamor prior, and it's shown in red. It's based on 3 meaningful regions across the area, I never know how, there we go, -3 to 1.5, and they're defined on -3 to -1, -1 to 0, and 0 to 1.5, okay? And so the other 2 priors that I'm showing you, a typical one would likely be the blue prior, a weakly informative prior across the area of the variable. And then the green prior is meant to be a mostly non-informative prior, so very flat prior across the area. So the one thing we need to do after we define our meaningful regions, we just need to set hyperparameters, okay, for the priors in them. And so let's say we have an interval from A to B, okay, that's our meaningful region. Then we're going to choose normal hyperparameters in that prior. So we're going to have a normal prior in that region. We're just going to take, for example, the midpoint of the region to be the mean of the normal prior. So that's what was done on the prior slide. If you looked, the normal distributions were centered inside each region. And then one idea might be to pick a parameter. Here I'm calling it omega. It could be 0.95, and what that would do is it would specify the variance in that region so that 95% of the probability in that prior is contained within the region, okay? It's important for this to be any different from using a weakly informative prior that my normal distributions and that multimodal density need to be separated. So you can think about kind of a repulsive mixtures approach trying to push things apart. All right. For our weights, phi, right here, we're just going to choose a symmetric Dirichlet prior. So one last thing that I'll introduce, and have a picture for this too, is that we're going to introduce some labels, and we'll call them S for our cluster, and rewrite our clamor prior in terms of the labels. And so all we're doing is we're coming up with a coding scheme that gives the profile of a cluster. So for example, if we have 3 variables of interest and we find 3 clusters at the end of the day, and the labels are 2, 1, and 3, or actually it doesn't matter how many clusters, the labels are 2, 1, and 3 for a single cluster, then we would characterize people in that cluster by having neutral values of the first feature, diminished values of the second feature, and high values of the third feature, okay? And so it might be easier just to look at this slide. Here we're assuming we have 4 variables and 4 clusters just for illustration. And here's an example of a profile matrix. Now instead of 1, 2, and 3, I'm just using sort of a triangle up for elevated, a triangle down for diminished, and a dot for neutral. So the profile matrix is just a collection of the meaningful region sequences across all the clusters, and we can read off a profile just by looking at one of the rows. So for example, cluster 2, the second row, has elevated temperature and diminished respiratory rate, diminished bicarbonate, and diminished albumin. If we look at the columns in the profile matrix, that gives us an idea of how much a given feature impacts the overall clustering. So for example, if we look at albumin here on the right, well, it's different, pretty different across the 4 clusters, giving us some information that it seems to be quite relevant for explaining clinical differences between our clusters. On the other hand, temperature may not be that informative. It seems to be elevated for everyone. So our ultimate goal is to inform treatment strategies. And for this purpose, it would be great if we had a short clinical checklist that could be used to classify patients and direct practitioners towards treatment options. So for example, something like high white blood cell counts and neutral bilirubin means that you have this type of subtype, which is best treated by a certain treatment. So, suppose we identify 5 clusters. If in each cluster, the mean levels of white blood cell counts are in the same meaningful region, then it gives us information that white blood cell counts may not be all that influential in determining cluster membership, so I don't have to leave that on my checklist for the purposes of making classification. So we will actually have a formal test in terms of a Bayes factor to test feature influence, and so I'll have a figure to kind of give you an idea, but basically our null hypothesis is that all our clusters have the same profile in terms of feature J, or really close to it. Okay, so if I have a lot of clusters, I might want to allow really close to it and not exactly the same profile. And so we can get a test in that manner. And I'll give you an example of that. Now, for people who work with clusters all the time, I just want to point out that this clamor prior is really easy to just drop right into your favorite Bayesian clustering Gibbs sampler. You're going to impute profiles, and then you're going to do updating, and it's not that hard to add to your current estimation scheme. Now, once we have our MC, a couple things though, it's good to marginalize out the weights for computation. Okay, so that makes things easier. Once we have our samples, we're going to get a point estimate of the clustering by minimizing an appropriate posterior clustering loss function. So we're going to use variation of information for this. It also will give us a credible ball on clustering that we can use to characterize uncertainty. All right, so now we're going to talk a little bit about the actual analysis. We're going to implement clamor. I'll show one result today, and I'll just tell you a little bit about the other with 2 different sources of meaningful regions specific to northern Tanzania. This is the one I'll be talking about, where we're going to use Matt and Ding's characterization of all 15 features in terms of what's diminished, neutral, and elevated in their population. This is very nice because the interpretations are directly tied to our features and clinical meanings of those features. We also ran a second analysis where we did the clustering based on meaningful regions in terms of the Seneca-derived clusters. The thing that's kind of tricky there is that there's a lot of overlap across those 4 clusters in many of the features, so it makes it a little more difficult to interpret when we use that sort of formulation. But it is more deeply and more directly tied to a prior result from the Seneca paper if we want to go that route. All right, so we're going to focus on the orange today. So let me give you an example of how this works. Let's think about blood urea nitrogen. Matt and Ding classified values of blood urea and nitrogen into 3 ranges: diminished, neutral, and elevated. Okay. If we look at the Seneca study, and Matt and Ding looked at those clusters, they said, well, values in this 1.5 to 5 range were characteristic of the alpha and gamma clusters in Seneca, and values above 5.5 were characteristic of the of the beta and the delta clusters. So that's the 2 different specifications you can see in each case. In the first case, I have 3 meaningful regions. In the second case, I have 2 meaningful regions. Within an analysis, it doesn't matter how many meaningful regions I have for each variable. So how does our hypothesis testing work? So let's stick with blood urea nitrogen. And remember, so I was going to do it this way, where Matt and Ding say values less than 1.5 are diminished, greater than 5.5 are elevated, and then in the middle are neutral values. And let's suppose we find 3 overall clusters. We actually find more, but I need to fit all the possibilities on a slide so my stat students will know what I'm talking about. All right, so we can characterize the blood urea nitrogen levels, the cluster profiles, as taking one of 27 possible partition values. And these range from, in all 3 clusters, in each cluster, BUN is diminished, to BUN is neutral in all 3 clusters, to BUN is elevated in all 3 clusters, and all possible combinations of neutral, elevated, and diminished across 3 clusters. So there are 27 possible partitions in this case, okay, if we have 3 clusters. If BUN is not influential in my clustering, then what I would expect to see is one of the yellow-orange clusters, okay? Sort of the same type of profile in BUN in each of the clusters. If BUN is influential, then I expect to see one of the white patterns on the screen. The Bayes factor is used to evaluate the hypothesis that BUN is not influential for clustering, okay? And so if it's not influential for clustering, we're gonna see orange. All right, so what did we get when we ran this in our population? So we used our prior, and we found that these 6 variables shown in yellow, so down at the bottom, white blood cell count, blood urea nitrogen, creatinine, AST, bilirubin, and albumin, were influential features in the clustering. The other features, things like temperature, respiratory rate, given these features, did not have a strong influence on our clustering. So what I'm going to do is walk you through the 6 clusters we found in light of these influential features in clustering, as well as other variables that include gender, HIV infection status, and mortality. Okay, so cluster 1 was the largest cluster. It contains over a third of the cohort. These people were characterized by having normal organ function and low mortality. And so here I'm also showing, in addition to the size of the cluster, I'm showing the gender breakdown, the HIV infection rate in each cluster, and then the mortality rate in each cluster. Those were not variables that we used in the clustering, but just showing them to you here so you can get a little more interpretability out of them, okay? This was similar to the alpha cluster in Seneca, except that in the Seneca study, there was, less than 0.1% of the patients in that study had HIV, and the HIV prevalence in this cluster was about at the average for the entire cohort, which I think was around 38%, okay? The second cluster was just under a quarter of the sample. This had the greatest fraction of HIV infection among the participants, and the probability of death was maybe a little bit elevated, and it had typically kind of neutral values of feature expression, elevated AST, decreased bilirubin and albumin, okay? So then we can go down the road and interpret more and more clusters. We can see this cluster 3. It has some characteristics of one of the Seneca clusters. It maps pretty well to the immune response and pulmonary issues cluster there. Clusters 4 and 5 are very interesting compared to the Seneca cluster. So one thing to note is that they're fairly small clusters for us. But what's really interesting is that these two clusters are characterized by having either liver in the case of one or renal in the case of the other dysfunction. But the mortality rates, and so in that sense, they map to clusters in Seneca. But the mortality rates compared to Seneca are flipped. So for example, we see only 8% mortality in this cluster in the 6th study, but it maps to a cluster in Seneca that had the highest mortality. And the same thing happens in cluster 5. This was our highest mortality cluster, and it maps to the lowest mortality cluster in Seneca, even though otherwise the interpretations of these clusters are quite similar in terms of liver or renal dysfunction. The 6th cluster was very small, and it was basically comprised of individuals who had just kind of a variety of values on the features. So this is one that didn't hang together as well. And it's really hard to say a lot about it. Maybe we'll learn some more. Our validation sample is going to be about twice the size of our current sample. And so we're hoping to learn a little bit more when we get a little bit more data to help us sort that out. So the other thing that we wanted to do, and Peter hinted at it in his remarks, right? You know, how good is this? Is it right? Is it useful? And so we took a variety of different clustering methods. So we didn't just fit clamor. We also fit, we also used the clamor prior defined a little bit differently in terms of the Seneca cluster. We also fit, standard Gaussian mixture model using priors like the ones Sylvia has used in her paper with Peter Green. We also use k-means and consensus k-means, which were used in the Seneca study. And we wanted to look at which patients seemed to be difficult to cluster. So either we had high uncertainty in our study about which cluster they belonged to, or patients who got put in groups that looked fairly different by different algorithms, depending on which algorithm we used. And so the first thing we see that stands out to me in this table was actually quite reassuring, and that's that we had a group of patients that had missing data on our meaningful features, and they were hard to cluster. So that's no big surprise, right? So if these are the variables that are contributing the most to the clustering, and we have participants with missing data on them, of course they're going to be harder to cluster. So to give you a sense of how strong this is, overall, 12% of the study participants had missing values on one or more of the influential features, but amongst those difficult to classify, 57% of them had missing values on these features. And so that's not at all a surprise. Now, amongst those with complete data who are difficult to classify, we do see a trend that may not be immediately apparent from the table, but it is if we plot different metrics from our data. They tend to be outliers in terms of the whole space of the 15 parameters. So they have odd combinations of the 15 parameters. They may not be an outlier in any individual feature that we've measured, but their combination of features is quite distinct. And that's a list that Matt and Ding have right now, and they're looking at in a little more detail to see if we can maybe fine-tune our model in order to do better for some of those patients. So to summarize, we've proposed clamor or clustering around meaningful regions. It's a Bayesian clustering method that models cluster centers. It's part of mixture models. We're presenting some default hyperparameter choices based on controlling the tails of Gaussian components designed to make our inferences more interpretable. Nice features are that you can easily integrate this type of prior into a standard computational algorithm, and it also allows us to evaluate feature influence to identify factors that are explaining our clustering structure. We applied clamor to our data from SICK in phase 1 with priors driven by normative biomarker levels and by a prior clustering in a different population. And we found clusters that were largely driven by organ dysfunction markers, and they correlated both with HIV status and with inpatient mortality. So with that, thank you very much for your attention and time today, and I'll take any questions you might have.
Thank you very much. Questions in the room to start with?
Are you picking?
Go on, Brian, throw it. What's an accident last year?
Oh, you've had accidents. We were wondering why it wasn't getting tossed around.
Thank you, Abby. That was a great talk. I'm curious about what you mentioned, that some patients can move to different clusters. So I wonder if that might explain why you see that some clusters might have different mortalities depending on a study, maybe progressing through different series of clusters. Is it possible, or were you able to match somehow, I don't know, the time from diagnosis or when you take the measures to make sure that, I don't know, that there is not a heterogeneity in terms of how long the patient has been ill?
Yeah, that's a great point. So the point, in case well, you're probably on the microphone. The cool thing about these data is we actually do have a lot of information about their experiences in patients. So we do actually have some amount, and I don't have the data yet, of longitudinal data about the progression. One other reason they may be a little different than the North American population is they're generally presenting sicker than our North American patients. You know, our North American patients and in high-income countries, people are tending to be older with chronic diseases, and so they're getting seen a lot more often in the healthcare setting, and so on an average, they're catching them earlier. That could be part of it. But yeah, we do have information about their whole sort of progression through the inpatient system. So we will be able to look at things like, you know, for example, twiddling with treatments, how these biomarkers are changing. I don't know that we have all of them that have been assayed, you know, from every blood sample that may have been taken from the patient. Certainly the clinical signs we'll have available basically at whatever resolution we'd like to have them. So that's a really fun project that I think will be really interesting to look into. Yeah, so definitely we're going to have some flip-flopping. You know, Matt and Ding have told me to expect that, and so it's not part of the original aims of our grant to do that, but that's definitely something that we're looking forward to doing once we check the boxes on the original 3 aims. Great stuff. Oh, look through it.
Thank you very much for that talk. I found it very compelling, the way of presenting the variables as being high, elevated, neutral, or low. Yeah. Was that sort of reaching such a way of communicating maybe with clinicians part of an ambition of your project? And does it work in terms of communication, or does it have restrictions in being it's just not? It's too simple. It's not conveying the entire picture.
I mean, I think it would be really hard using, we had a talk about this earlier this week, the full range of the variables in order to derive the clusters. And often what you see is kind of minor clusters that get picked up that maybe explain variability in the data, but maybe it's not variability that's clinically meaningful. So we're trying to push towards solutions that are more clinically meaningful. And so the one challenge I see in this type of approach is the definition of clinically meaningful could vary from setting to setting. And so the reason we got this idea in the first place was our first thought was, great, the Seneca study did exactly what we want to do. Maybe they used a different clustering method, but they published, they were really lovely in their publication, because they published all the clusters and they published the 15 features and the mean value of each feature in each cluster. And so we thought, perfect. What we're going to do is we're going to structure our prior so that we have all 4 Seneca clusters built into our model, and we've stuck them there. And then we're going to see if we see any evidence of new clusters in our data or not, because we know, you know, we have these clusters that's from 63,000 individuals. Why would I throw away data from 63,000 people? Well, we were really disappointed. So what happened was, for the statisticians, in order to preserve the interpretations of the original Seneca clusters, we basically had to put point nest priors on the centers. So we had to allow no changes in the clustering structure at all. And then when we did that, all the algorithm did is create new clusters to put our new patients into. So, so the moral of that story was these exact same clusters are not going to hold up, you know, in a population that's so different. So based on that, we went to Matt and Ding and said, you know, can you help us with what we think is typical for these values in this population? For example, we have variables like age. We know age is going to be really different in the 2 populations. We know HIV prevalences or CD4 count is going to be really different. Those aren't values we used in the clustering here. And so they define those regions, I mean, those meaningful regions based on literature and on their own work in that kind of population, you know, to be relevant right there. So it would be a little difficult if I have another data set, you know, in Durham, North Carolina, where I live, I'll have meaningful regions that may be a little bit different, for those features in our population, which is going to be sicker and older, to draw conclusions. So, yeah. So it's not perfect. We hope it's better.
We have a question online from Sheila. Sheila, are you able to unmute and say your question, please?
Oh, thank you very much, and thank you for a super lecture. I wondered if there is any sense at all in applying the clustering separately for those who are known to be HIV infected versus those who are known to be uninfected, and perhaps you have a third group where HIV status is not known. The reason I suggest that is that HIV disease, particularly when the patients are hospitalized, tends to derange markers quite considerably.
Yeah, that's a great point. So, so for this population, we do know HIV status on everyone. We have the CD4 count for everyone who's infected, as well as for some people who weren't. But the sample size is small. So I think the biggest challenge of that is that we have almost a 40% infection rate and a sample size of 288. So I think in this direct population, it would be very difficult to explore that. I think once we get the prospective study, which should finish recruitment in December of this year, we've got 500 people already, so we're hoping to get, a few more. And in that case, we could end up having, a sample of uninfected individuals of roughly the same size as we have in this study, and that would be really interesting to look at there.
Thank you.
Thank you.
Thank you for a great talk. So I have a question which is maybe related to the last answer you were giving. So I do similar work to what you just described, and one of the difficulties we often face is assessing the reproducibility of clusters in different populations. And even when you have sort of demographically similar populations, it can be really hard to do that, and implicitly or explicitly you have to do some kind of cluster matching, which might be really challenging. And I just wondered if you had any thoughts on this, and in general, some of the challenges of reproducibility and clustering analysis.
Yeah, I think, that's one thing that David and I have actually thought about a lot, because clustering in general is what we would call brittle. You can have small perturbations in the subjects in your study and see, unfortunately, uncomfortably large differences in your answer. And so one thing we're doing to address that is that Matt Brubach, who's the PI of this study, was really brilliant in being able to capitalize on the Indite study, which, again, they're not all sepsis. It was febrile deaths, but they had a registry of patients for whom we were able to identify, not all of them died, patients who we were able to identify using a validated scale. Okay, they had were likely to have had sepsis. So we do have an internal comparator that we can use. One approach might be we could just look at endpoints like, for example, mortality in the current study once it's ended, and see how well our current clustering structure predicts mortality. The challenge of that, it's a good problem, is that our mortality is a lot lower than we thought it would be. So yay, the statistician in me maybe has a small boo, and that we have fewer events. But no, yeah, it's really, it's good that we have fewer events. So we'll be talking to Matt and Ding about, is there anything that we can use short of mortality in the medical record to maybe give us some sense of a meaningful sort of outcome marker that we could use. The other thing too is that we could just reproduce the exercise in the population. In fact, we could fit the models together in order to make comparisons. And I see David's got a comment.
I guess the other thing we've been doing a lot, and we have like a new NIH R01 motivated by that, and that's sort of what Alex is doing largely for his dissertation, is to define model-based clustering methods that are intrinsically less brittle, and so they're much less brittle to the kernel choice and cluster splitting problems that you run into. One direction in that regard is this type of the Corson Bayes or C-Bayes that Jeff Miller and I worked on in the past, and a lot of people are using that to obtain more robust clusters. And Alex has also come up with, smart Bayesian decision theoretic approaches. He just got a positive review of JASO on that. Initial paper on that thread for robustifying clustering using normal mixtures or something to decrease the brittleness improve reproducibility across studies.
Yeah, one big challenge, one easy way to see clustering fail is if in this Gaussian mixture model, if you have a variable that's not Gaussian, then you can divide the cluster trying to make it look more, because I can just break data down and put little Gaussians everywhere and make things, fit my model better. But that's not the behavior we want to have. So. But that's a hard problem. And yeah.
Fantastic talk. I had a question about the prior centroids, look how you're doing it. Did you ponder about using some sort of graph-based segmentation, like let's say as spectral clustering sort of thing, because for coming up of these regions?
No, so the only thing we've done so far, so basically where we came at this from was from trying to use, trying to make it take advantage of the Seneca study with 63,000 people and what we thought were fairly robust clusters because it was so big. So we've really only come at it from the perspective of using clinical information to try to help us determine those regions, as opposed to trying to use something, more sort of theoretical, and from a statistical or mathematical perspective in order to help us do that. We'd have to think really carefully about identifiability in that context, but yeah, that's a great suggestion. Thank you.
Is it me? I'll go to mine. Sorry.
Oh, there you are.
Yeah, hello.
I saw your hands up at the very beginning.
So I think
Now you're going to get me back
always
for my last move in the game.
Yes. No, we're
Not that we're competitive.
We were friends before. We're friends after.
Okay, that's right.
Sorry, I was wondering about these meaningful regions in terms of thinking about prior elicitation with experts. As I understand it, the regions you define, they don't have to. They could overlap. Or they could be disjoint, can't they?
Yeah, so
when you're trying to get an expert to give them to
yes, and that's an issue when we define the regions based on the Seneca clusters. So for example, the alpha and gamma Seneca clusters might have both, elevated temperature, for example. So it is possible that they overlap. I think the method works less well. So one thing we did to get at that, and this is something we're still thinking about, but one thing I got nervous about was, look at systolic blood pressure under 120 is, great, right? And what we said we'd do and what Alex first programmed was, okay, I'm going to center it, at 60 and throw a normal there. And that's not like a great value, right, for systolic blood pressure. And so there were kind of two solutions we had to that. The first thought I had was, okay, what if we do a truncated normal? But actually that, and truncated at 120, right? Because mostly probably in that group, the mean's going to be pretty high. But that didn't give us enough separation in the prior. So it sort of acted more like you would have a weakly informative prior. And then it didn't see enough separation between those regions in the prior. So the idea is that you do need to have some separation, like they're overlapping. I'm only having 95% of the mass on average in one region. But I need to see some space, some air between the modes and the prior. And so what we ended up doing is centering the prior at 100 or something like this with a smaller variance.
So what happens when you have two experts trying to give you two different sets of
regions? So ideally, a mixture of experts, claimer model, I don't know. Ideally, these were, we did, systolic blood pressure in the US, I don't think there's too much, we might argue, certain components, but that's sort of well settled. Some of these other things are less well settled. And so in that case, I would run the clustering both ways and hope, and so what we did is we just had a classification matrix where we looked at, okay, who are the people that get clustered one way in one scheme and one way in the other scheme? And oftentimes it's just the people we had a whole lot of uncertainty about where to cluster them anyway, because the fact of the matter is, really, everybody's unique and we have 288 clusters of one in our data, but we're trying to group people, in different types of hammers, but put all our hammers together, as Brendan was talking about this morning, so that we can come up with treatment strategies that might work, well for everyone in a similar group.
Can I be cheeky and ask to abuse the chair's privilege? Because I was thinking something similar to Sheila and about HIV, and then I was trying to expand that in terms of, all these people have a past health history, and at least for Seneca, you have a lot of information on that. So to what extent are your, I'm going to call them biomarkers, explained by the health history or the interaction of the health history and the sepsis cause.
Yeah,
Now, they may still be useful because you can measure them quickly,
sure.
but does thinking about that actually help you at all?
Yeah, so we don't have access actually to the raw data in Seneca, just to the means. But it's true, especially if you get outside the United States, you might actually have a complete health history of your patient. And so I think, and that's one thing we'll look at a little bit in terms of, we were talking about, somebody's prognosis, or their progression as an inpatient. But certainly they might have, underlying features that are influencing some of these variables that are not necessarily reflecting responses to sepsis. Now, maybe those underlying features are dictating what treatments might be more or less successful, with those patients. And some of them could also be related to the organism,
Yes.
at play that's causing the infection as well. So that's actually where I got interested in this work, was with Indite, and they were trying to look at febrile deaths in Tanzania and see what caused them. And so they were doing extensive autopsies on the patients to try to, of course, there's lots of bugs in your body, not just the one that killed you, but the idea is to try to figure out the actual cause of death. Because in general, in Tanzania, it's coded as malaria because there's no stigma attached to malaria. The mosquito got you. And so they tend to, if you die with a fever and it's a malaria endemic area, it just gets written down as malaria. And then the family doesn't have to worry about there being any sort of, concern about what really went on. So that's a great point. Yeah.
Yeah, so my question exactly relates to that point, because one of the reasons that clinical trials that have been tried in sub-Saharan Africa failed is because of chronic malaria, how it immunomodulates the population. So did you exclude malaria from your patient cohort?
So I would have to check, I would have to double check. I assume yes, because Matt and Ding were the ones who helped us create the criteria to go into the, clustering algorithm, but I'd have to double check to be 100% sure for that.
Do some of those patients look like they've got falciparum from malaria? I'm sure they're pretty good at diagnosing that in Tanzania.
Sure, but could be.
Any more questions? We have a little bit more time. We've got one at the back.
Okay.
Can you?
Are we brave enough to toss it? All right.
Okay, cheers. Thanks, Amy. Yeah, I just wondering, because right now I get a lot of the data, like a blood indicator data from Cantonese, and so I just wondering, as we all know, the gender is very, influence the different disease or something, and should we separate the gender, male and female, to cluster the data? And I have a second question about the, do you have the healthy data to compare with your disease patient? And the third one is I look at the 6 cluster table, and I look at the indicator have the change when you're analyze them. And did you detect the data from the different time or something?
Oh, okay. So let me try to remember. So first is gender. So I guess the first answer would be the same answer I would give for HIV, which is just that the sample size gets small. So once we divide 288 in 2, I think we get a lot less robust clusters. Gender is actually really complicated, and I would have to sit down with Matt and Ding and think about that a good bit, because what we see in this population, for example, is a lot of differences in access to care and patterns of healthcare by gender. So for example, women in the study, or women in general in our catchment area, are seeing doctors fairly regularly because of pregnancy. So when they go in and they're getting their prenatal care, one of the first things that happens is they do an HIV test. And so if you look at HIV diagnosis, it's happening much younger in women because they're going in without symptoms of HIV, but they're getting the test because they're pregnant. There's no such similar thing for men. So they're not going in asymptomatically for HIV testing because of something else in some sense. So women presenting with HIV tend to be less sick and tend to respond better because they're caught earlier than men. So there's some patterns like that around gender that Matt and Ding would have to talk to you in more detail about, but I think we'd have to be careful that we weren't, by separating by gender, also separating by other things, you know, for example, like access to care and things like that. That's okay. The second question was,
the compare with the healthy data.
oh, healthy data. Yeah. So in this study, we have a subset of indite patients, and they're not healthy. So we do not have healthy controls in this study at all. So so I don't have those data. We did have in indite a subset of patients that did not die with fever, for whom we got verbal autopsy, because the goal of that study was to figure out what killed you. And for example, there's all sorts of bacteria in my nasal cavity or in my lungs or in my gut, and whether they belong or not sort of depends on where they are and things like that. But those patients don't necessarily have the blood sampling done to get the biomarkers that we have. We might be able to get things like temperature and such, but we wouldn't be able to get those other biomarkers for that. And then you asked a question about the 6th cluster, but I didn't quite understand what you were asking.
The third one,
yeah,
is the change of the indicator, increase and decrease in the on the table. And yes,
I sort of think that 6th cluster is 10 people. And so I have a hard time, I worry about over-interpreting anything we see. So certainly I can use the increase and decrease to tell you where the center of that cluster was, but I'm not really confident in that 6th cluster. When we look at the probability of assignment to that cluster, those patients, we had the most uncertainty around where to assign them. So they're not assigned to that 6th cluster. I mean, it's, you know, right, like higher probability than the other clusters, but it's not all that high. So I would be really cautious about interpreting that. And I hope that when we get, you know, maybe twice the sample size from the inpatients that we have now, we'll be able to learn a little more and see, maybe it goes away, you know, once we have more data, or maybe it becomes more clear what that represents. But I wouldn't really interpret any of those symbols with any confidence.
Okay, sure.
Yeah, that's a great question. I'm glad you pointed that out. Yeah. Oh, you can use the real one. Yeah.
Which is, I mean, like, given the informative priors and
stuff,
so do you have any sense what the prior on number of clusters looks like?
So the way so what we did is we did an overfitted finite mixture model. So we set an upper bound at 10 to be really conservative, but the number of clusters is really going to be driven by the loss function we use to assign them. And we're using variation of information, which is gonna be pretty stringent in pushing the number of clusters down. So if you used a different loss, you would get a different number of clusters. We haven't done any sort of theoretical derivations on that yet, but in general, we found that in most of my, it's recorded. There might be an alternate universe in which many times individuals don't want to deal with more than 4 clusters. You know, like I think there becomes a point at which the clustering is not that useful, it's not that practical, and so so we tended to use the loss function to try to drive it down to make it more interpretable, and we got to 6. So yeah.
Okay.
I've been told previously, come back when you have fewer cluster, you know, sometimes.
Something I can think about.
Yeah, and I mean, anybody who's done clustering, Brendan talked about this a little bit before, knows it's a great way to pick up outliers, you know, and you'll find these singleton clusters and things like that in the data sometimes. So, but you have a question.
Yeah, so I quite like this clamor prior, right? So it's a way to sort of try to induce some sort of meaningful interpretation of your clusters.
Mm-hmm.
And you set sort of these cutoffs for elevated and neutral and whatever, and then you had this omega parameter controlling the mass of the distribution inside this thing. And then you did that for each of your 15 covariates. And then my question becomes, well, now the joint prior over that, is that just the product of those 15 marginals?
So the prior, So the prior is going to be specified on each cluster center. So we are assuming independence across the clusters. So we'll have a form like that, yes.
So does that mean, for example, that if you have if you have two covariates of interest, you have sort of three categories with three normals centered. Then you have in the other direction you have three as well, and so you get. I guess the thing I'm trying to get at is that when you then look at the sort of induced joint density of that, if you will have sort of regions in your space now that's very lowly, that has basically zero mass, because you're now producting together things that basically have zero mass.
Yeah, I know what your question is. I think that's the answer to that is yes. I haven't thought about it in a lot of detail, but yes. I think in any prior structure, you're going to have regions with low, yeah. And
so then when you go to sort of, you had some patients that were really difficult to place in clusters. Could that be because they exist basically in these very low probability regions?
It could be, yeah.
Okay.
Yeah, and that would happen in general if we use like the weakly informative prior, people who are in the tails.
Yes.
You know, so that's, sure. It's not unique to this construction necessarily.
Okay.
It's a more general, yeah.
Because I was just curious, because you have since you have these three sort of centers, you have this omega parameter giving you the space between the centers.
Yeah.
That you're sort of now in interesting areas between clusters. You're creating low probability regions.
It's not no mass, you know, so it's like 2.5. I mean, if I pick omega as 95%, right, it's gonna, or 0.95, it's gonna be 2.5% and 2.5% of the two neighboring Gaussians, which is plenty to move around.
Okay.
Yeah.
All right, thank you.
Yeah, just a couple clarifications on that. So, I mean, if the usual problem you have if you have just this kind of product of independence is then you have these kind of circular clusters, and then you tend to over cluster. Yeah. And I would say you still do that a lot, even with variational information loss. And so we didn't get that so much. I mean, we had an upper bound of 10, and then we induced 6 clusters. And so even though we have this kind of overly simple for interpretability reasons, we're trying to put independence, you know, and it would make sense to have like some multivariate normal or something, and have dependence have more elliptical shaped clusters. But it didn't seem like that was needed for these data, and it certainly makes the interpretation a lot more complicated.
Yes, it does. Yeah, immediately. Yeah. Thank you.
But it might make sense to step back and specify some priors in a broader sense for combinations of variables too. I hadn't thought about that. Thanks.
But it seems also, for what you told, that you put much more thought into specific priors for some numbers of clusters than for others. So this specification for 10 clusters, for example, is going to be a very different prior to the one with very clear 3 modes for 3 clusters.
Oh, well, in this case, we have either 2 or 3 modes. So for all the, because I think they put SBP in 3 groups, not in the US classification. So for most of the variables, the investigators either had like elevated, neutral, and diminished, or they had, you know, out of range, in range type of interpretations, you know, low, high kind of things. So,
there's 2 types of clusters.
Yeah. Sorry. There's clusters in the sense that you can think about the clamor prior as being a mixture itself, you know, of elevated, neutral, and high, where I have a normal on elevated, a normal on neutral, and a normal on high. And at the end of the day, I'm trying to cluster all my predictors into clusters of people, you know, and so 10 is the upper bound on the number of clusters of people. In the prior construction for like, you know, bilirubin, and I'm calling that low, medium, and high, I'm fixing 3 kernels there. So I'm saying there's 3 low. There was a question about, can we try to, he's gone, but there was a question about, can we try to learn this adaptively? But what we're doing is we're saying, you know, Matt and Ding say there are 3 regions, low, medium, and high. And so we're not searching for that number of clusters. We're only searching for the number in the people.